Okay, going to be working on 10.4, 10.5, which is the section on equations of lines and planes, a very important section. And we're going to start out with number one, which is a series of true and false questions. I thought about maybe just showing you one of these or two of these, but I think I'll just talk about all of them. So let's discuss this. The first problem says, part A for number one, true or false, two lines parallel to a third line are parallel. So two lines that are parallel to a third line are parallel. So let's say we have two lines that are parallel. So we have two lines. The fact that they're parallel means that they point in the same direction or possibly in opposite directions. They just have to be scalar multiples of one another if you look at like the vector that points in that direction. So the direction of this line must be a scalar multiple of the direction of this line. So if these two lines are parallel to a third line, that means this one is parallel to this one, which means it's a scalar multiple. The direction of this is a scalar multiple of the direction of this. Then this line is also parallel to this green one here. Then it's a scalar multiple. The direction of this is a scalar multiple of that one, which means that these two have to be scalar multiples, which means they're also parallel. So it's true. Now, part B says two lines perpendicular to a third line are parallel. So if you have, let's say you have this green line and you have a line that's perpendicular to it, and then you have another line that's perpendicular to this green line, does that mean that these two here are parallel? Well, that's pretty obvious that that's false. So look, these two lines are perpendicular to the green one, but not parallel to one another. So it's false. C, two planes parallel to a third plane are parallel. This is true. So if we take, let's say this board is a plane, and I have another plane that's parallel to it. So it would have to be like this sheet of paper, it would have to be parallel. And if we have another plane, which, let's use this, another plane that's also parallel to this board, then it must also look like that. So these two planes must be parallel to one another also. So that's true. D, two planes perpendicular to a third plane are parallel. So if we have this plane again, right? And I have a plane that's perpendicular to it. Let's say that, okay? So remember this sheet of paper, I'm just gonna come in, let's say that's perpendicular. And I have another plane that's perpendicular to this board. Does that mean that these two have to be parallel? And you can see pretty obviously here, if I just turn this one like this plane is still perpendicular to the board, this one's perpendicular to the board, but these two planes are not parallel to one another. So that's false. E, two lines parallel to a plane are parallel. So we'll do this again. We'll use the board as a plane. I have two lines that are parallel to the board. So let's take this line here, and I'm just going to flatten it out so that it is parallel to this plane. And then I'm going to take another line, and let's say like this, it's also parallel to this plane, but these two lines are not parallel to one another. So that's false. That was E. F, two lines perpendicular to a plane are parallel. So if I take this plane and I give you a line that's perpendicular to it, it's this, then I give you another line that's perpendicular to it, let's say this, then there's no way I can move these around. These are always going to be parallel to one another. So that's true. G, two planes parallel to a line are parallel. So let's take the board as being a plane. and let's make it this plane, let's make it parallel to this line. Okay? And now let's take another plane, I'm going to tilt this, another plane that's parallel to this line, which would be this. Okay, notice that they run in the same direction. And when I take this and flatten it out, it's in the same direction as that plane. These two planes are not parallel, so that's false. H, two planes perpendicular to a line are parallel. So here's a line. I'm gonna make this plane be perpendicular to this line. Okay, and then I'm gonna have another plane that's perpendicular to this line. Now the only way I can do that is maybe if I put this on the top. That's the only way. And so notice that when I put this here, this plane and this line are perpendicular. This plane and this line are perpendicular. But this plane and this plane are parallel, so that would be true. Again, it was saying two planes perpendicular to a line are parallel. Part I says two planes either intersect or are parallel. So if I take the board as being a plane, and I imagine a plane that's parallel, another plane, either these two planes are parallel to one another, which means that they run, there's a little gap between them, and they never intersect each other. Or if they're not parallel, I tilt one a little bit, then eventually this plane will come in and intersect that plane. So two planes are either parallel or they intersect each other. That's true. F says two lines either intersect or are parallel. So if I have two lines here, right, they could of course intersect each other, right? They could be parallel, but are those the only possibilities? Well, how about this? In three-dimensional space, these two lines right here, okay? So instead of hitting each other, I just raise this one up a little bit. These two lines are not going to intersect each other, and they are not parallel, as you can tell. So it is false. Part K says a plane and a line either intersect or are parallel. So a plane and a line, here's a plane, here's a line. If I just run this line and bring it off the board, then they are parallel, right? So they won't hit each other there. Or I could possibly tilt the line a little bit, and then eventually that line would go and punch a hole through the plane. And there's no other way I can do this. They're either going to be parallel or at some point they're going to hit each other. So the answer for that one is true. A plane and a line either intersect or are parallel. All right, that's just foundational stuff. Let's move on to number 3. So number 3, we want to find the vector equation of the line, and the parametric equations for the line through the point let's see, they give you a point 2, 2.4, 3.5. And parallel to the vector 3, 2, -1. So remember, when it comes to lines, vector equations of lines, we need two things in order to determine the vector equation of a line. I'm going to put it up here. The vector equation of a line, RT, equals the vector R0 plus TV. Let me make sure that's the same formula I'm using in the notes. Yes. Okay, yeah, that works. All right, so R naught here is a vector, and it represents, in two-dimensional space, it's easiest to show. If I have a point that's on the line, R naught is the vector from the origin to that point. In other words, it's just a point on the line rewritten as a vector. And then V in the problem is the direction of the line. Okay, so that's some other vector that shows me the direction of the line, and then of course the line extends forever in both directions. So this is our V. So that's what we always need in order to determine the vector equation of a line. We need a point that lives on the line, which we will convert to the R naught vector, and we need a direction of the line, which we will replace right here with V. We will put in here for V. So what do we have here? We're given a point on the line right here. Okay, so we have a point, good. And I must be parallel to this vector, which means that my line must run in the same direction as this vector runs. So whatever this vector is, 3, 2, -1, whatever it is, my line must run parallel to that. So these two direction vectors are equal, which means I can use this for my V. And so it's just going to be a simple plugging in here. R naught is the vector, which is this point converted to a vector. And then of course V, the direction, is 3, 2, -1. Now I can use any scalar multiple of this, but I'm going to just use the vector itself. So now I just come over here to write down the vector equation. So the vector equation is going to be R of t equals R naught to 2.4, 3.5 plus t, and then the direction vector 3, 2, -1. I'll distribute the t through. So 2.4, 3.5 plus 3t, 2t, -t. And then I'll add these two vectors together. So when we add two vectors, we just add their components. So 2 plus 3t gives me 2 plus 3t. 2.4 plus 2t, and then 3.5 minus t. So this is the vector equation of the line. Of course, t here is an element of the real numbers, which means that if we start plugging in all the different values of t in here, we will draw the line. Now, that's the vector equation of the line. I also need the parametric equation. So the parametric equation is very easy to get. All you have to do the parametric equation is just write down x equals, y equals, z equals, and x will be the x component, y will be the y component, and z will be the z component. So there are your parametric equations, and that's it, we're done. Let's look at number 4. Want to find again the vector equation and parametric equations for the line through a point. So it's number 4. Find the vector equation of the line through a point. So they give you a point again, that's good. The point that they give you is the point 0, 14, -10. So the point 0, 14, negative 10. And then they say it's parallel to the line, and then they give you the parametric equation of another line. So x is negative 1 plus 2t, and y is 6 minus 3t, and z is 3 plus 9t. So remember, all we need to figure out the vector equation of a line is r naught, which is a point on the line converted to a vector. So we already have that. Okay, so we can use that. All we need now is the direction of the line. And if we're going to be parallel to this line, then we could just be pointing in the same direction as this line. So what is the direction of this line? So just remember where these come from, right? Remember, this is a separate line than that line. They're not the same lines. They're pointing in the same direction, but they're not the same line. So where do we get the direction from? Well, when you look at the parametric equations, it's going to be the coefficients of in front of the t. If we create a vector, v, over here, and it's 2, negative 3, 9, then it will point in the same direction as this one. Now, just to reiterate, if I were to take this back and try and rewrite this as a line in vector, the vector equation, I have negative 1 plus 2t, 6 minus 3t, 3 plus 9t. And then what I could do is I could split that up, negative 1, 6, 3, plus 2t minus 3t, 9t. And then negative 1, 6, 3, plus factor a t out, t, 2, negative 3, 9. So this line right here from these parametric equations, if we switch it back to the vector equation, it would be this, well, this, but notice that if we decompose this and go backwards, this right here, 2, negative 3, 9, is the direction vector. This is like the v. So that's why all we have to do is look at these numbers. And so we've got everything we need. We just write down r of t equals our point converted to a vector plus t times 2, negative 3, 9. And then put everything together. T times 2 is 2t. Add 0 to it, we just get 2t. T times negative 3 is negative 3t. Add 14, so 14 minus 3t. And then t times 9 is 9t, and then subtract 10. So I'll go negative 10 plus 9t. That is the vector equation of the line that is parallel to this line and runs through that point. Of course, t here, again, is an element of the real numbers. All right, now the parametric equations of this line are going to be just the x, y, and z component respectively. So the parametric equations are x is 2t, y is 14 minus 3t, and z is negative 10 plus 9t. So if we come back and we compare it, okay, let me compare it over here to this. This was the line that we had to be parallel to. Notice that this line and this line, two different lines, they have something in common, right? They have the 2t, negative 3t, and 9t. That's because they're parallel. The only difference is this negative 1, 6, 3, that's a point that lives on this line, and that point does not necessarily live on this line. So 2, 14, negative 10 lives on that line, which, I'm sorry, not 2. There's a 0 next to this. 0, 14, negative 10 lives on that line. And that point does not live here. So you can see that these are two different lines. They're just pointed in the same direction. Okay, so that's got number 1, 3, 4, let's see, 5. Same thing. Find the vector equation of the line through the point. So they give you a point again, 1, 0, 6. And perpendicular to the plane. So perpendicular to the plane, x plus 3y plus z equals 5. Make sure I got that right. Yes. Okay, so we have, let's try and draw a picture three-dimensionally. We have a plane, right? Sheet of paper here. We have a plane sitting there in space. And we have a point sitting in space somewhere, wherever it is. And what we're trying to do is find the vector equation of the line that goes through that point, but is perpendicular to this plane. So imagine again, we have this plane sitting in space, and we have some point sitting there. What we need to do is imagine dropping straight down to this plane through with a line that runs perpendicular to this plane, trying to find the vector equation of that. So let me move that point just a little bit so it makes a little more sense. You know, I could have a line that goes like this, punches through here, and then keeps going. But obviously that line would not be perpendicular to the plane. I could have a line that goes like this, punches through here, again, would not be perpendicular plane. I'm trying to find the line that goes through here, punches through, keeps going, and is perpendicular to this plane. So what we notice is that we have a point, right? So we have a point on the line. That's good. All we need is the direction. So this blue segment here, the direction of that, right? The direction of that, I could call my V. That direction is parallel to the normal vector that comes out of the plane. So remember that all planes have a normal vector, which is a vector that points out of the plane, right? Runs perpendicular to it. And since this normal vector is perpendicular and the direction of our line needs to be perpendicular to the plane, I can actually use this normal vector as my V. So if I let my V be the normal vector, then I have the direction. The only question that remains is what is the normal vector of this plane? And that's easy to do because the normal vector, if we have the equation of the plane written as follows, the normal vector is just the coefficients of the x, y, and z variables. So the normal vector of this plane is the vector 1, 3, 1. And therefore, okay, 3 dots means therefore. Therefore, I'm going to let my direction vector be the same vector, the direction vector of my line. And that way I'm running parallel to the normal, which is also perpendicular to the plane. So that should be all I need. I'm going to write down the direction, or the vector equation of the line. So I need my r naught, which is the point on the line converted to a vector, plus t times the direction vector, which is 1, 3, 1. And then we can combine things together. So 1 plus 1t, so 1 plus t. 0 plus 3t, so 3t. And then 6 plus t, so 6 plus t. And then t, again, is a real number here. So that is, this right here is the vector equation of the line that runs through this point and is perpendicular to this plane. And now I just want to get the parametric equations. So for the parametric equations, 1 plus t, 3t, 6 plus t. Done. And that was number 5. Okay, find for number 7, I believe. Now we're doing 7. Number 7, find the parametric equations and symmetric equations. So I want the parametric equations and symmetric. Of line through 2 points. Through the point, or through the 2 points, 0, 1, half 1, and the other point, 2, 1, negative 3. So sitting here in 3-dimensional space, I've got some points, 0, 1, half 1, so some point here. I've got 2, 1, negative 3. So I've got a line that goes through these 2 points. And I need to come up with the parametric and symmetric equations. So what I'm going to do is I'm going to first try and find the vector equation. Okay, so we need a point on the line. We actually have 2 points, right? This is the point 0, 1, half 1. This is the point 2, 1, negative 3. And so I need one of those points. I can use either one. So I'm going to use this one because it doesn't have any fractions. So I'm going to let my R0 vector be the vector 2, 1, negative 3. And then the only thing left is to find a direction, the direction of this line. And when it comes to direction, it's a vector that points the same direction as this line. I can simply take the vector that goes from this point to this point, or the other direction. It can go the other way too. But I'm just going to pick that one. I'm going to call that one V. So what is V? Well, V is going to be, we know how to do this. We're trying to get the vector from this point to this point. We take 0, we subtract 2, negative 2. We take 1 half, we subtract 1, we get negative 1 half. And we take 1 and we subtract negative 3, which same as adding 3, we get 4. So there's your direction. So now we can put it together and we can get our vector equation. So R of t is equal to, let's see, I wonder how fast you can do this. Remember, it's going to be R0, which is this, plus t times this. So if we multiply this by t, I'm just going to get little t's in there. And then when we add these two together, we get 2 plus this, so 2 minus 2t. And then we get 1 and then this, so 1 minus 1 half t. And then negative 3 plus that, so negative 3 plus 4t. So there's the vector equation of the line. And I need the parametric equations. So we've done this already. I'll write them down. X will be 2 minus 2t. Y will be 1 minus a half t. And z will be negative 3 plus 4t. There we go. So there's your parametric equations. So vector equation of the line, parametric equation of the line, and now we need the symmetric equations. So to do the symmetric equations, all we do is take each of these and solve them for t. So if I take this and solve it for t, let's see, I'll move, it depends on how you want to do this. I'm going to move the positive, the 2 to the other side. And then I'm going to divide by negative 2. So when I divide by negative 2, I get negative 1 half x. So divide that by negative 2, divide that by negative 2, I get plus 1 equals t. All right, now I'm just going to save that for now. Same thing here, I'm going to solve for for t, so I'm going to get y minus 1 equals negative 1/2 t. I'm going to multiply both sides by negative 2, so negative 2y, and then negative 2 here is positive 2 equals 2. And then I'm going to solve this one for t. So z plus 3 equals 4t. Divide by 4, we get 1/4 t plus 3/4 equals t. So since this equals t, this equals t, this equals t, then what I do for my symmetric equations is I write down negative 1/2 x plus 1 must equal this, which is negative 2y plus 2, which must equal 1/4. Oops, this should have been, hold on, z, oops. 1/4 z plus 3/4. So this is your symmetric equation right here. And that's number 7. Yeah, my answer looks a little different than the answer in the back of the book, but it's correct. It's the right answer. Okay. Number, what do we have next? Number 8. Same thing, same instructions. Find the parametric and symmetric equations of the line through the point 2, 1, 0. So you're given a point 2, 1, 0, and it's perpendicular to I plus j and perpendicular to j plus k. Okay. So what is I plus j? I plus j is just the vector 1, 1, 0. And j plus k is the vector 0, 1, 1. So what I need to find the vector equation of the line, right, is this. I need a point, which I've got, right? So I know that r of t so far is going to be 2, 1, 0. It's the point on the line converted to a vector, plus t times, now I just need to know what v is. V is the direction of the line. Well, this line, okay, has to be perpendicular to this and perpendicular to this. So I need to find a direction, right? We've got 2 vectors sitting out here. I plus j is sitting there. We've got j plus k, which is sitting there. We can put them tail to tail like this. So wherever they are, they're sitting out in space, right? My line needs to run perpendicular to both of these. So I need to be perpendicular to both of these vectors at the same time. Well, that's the value of the cross product, right? If I give you 2 vectors and we are asked to get the cross product, when we cross these 2 vectors, let's say I cross this vector into this vector, then the right-hand rule, I'll have a vector that's coming out towards us here, and that vector will run perpendicular to both vectors. All right, so if I'm trying to find a vector, v, that's perpendicular to these 2 vectors, all I'm going to do is cross these 2 vectors. That answer is perpendicular to both, which would be a perfect candidate for v. So I'm going to let v be equal to 1, 1, 0 crossed with 0, 1, 1. And let's go ahead and do that cross product. Now, I wrote them vertically here, so it'll be a little easier for us to do. If I'm trying to find the I component, cover up the I. Okay, 1 times 1 is 1. Take away 0, so I just get 1. Cover up the middle. We've got 1 times 1 is 1. Take away 0, and then subtract that. So it's going to be negative 1. And then if we're trying to get the last piece, cover this up. 1 times 1 is 1. Take away 0, so 1. So that's going to be our v. So we come back over here. 1, 0 plus t times v, but v I just found was this, so I'm going to multiply t through to each of those. So t, negative t, t, then add together, we get 2 plus t, 1 minus t, and just t itself. So that's the vector equation of the line. The parametric equations are 2 plus t for x, y is 1 minus t, z is just t itself. And now to get my symmetric equations, I just solve each of the parametric equations for t. So solve this one for t, I get x minus 2 equals t. Solve this for t, move the t to the left and the y to the right, 1 minus y. Solve that for t, it already is t, so z. So I hope I didn't do that too fast. Just solve each of these for t, set them equal to each other, you should get that. And that was number 8, just verify here. Parametric 2, 1 minus t, x minus 2, yes, negative y, 1, z is, yes, okay, we're good. All right, that's number 8. Let's take a look at number 10. Same instructions, find the parametric and symmetric equations for the line that, let's see what information they give us. The line of intersection of the planes x plus 2y plus 3z, x plus 2y plus 3z equals 1, and x minus y plus z equals 1. X minus y plus z equals 1. All right, so we've got two planes sitting out here in space, all right? We've got two planes. Let's say it's this wall and this plane. And I'm trying to find the vector equation of the line of intersection. So here's where they hit each other, right? And imagine this line goes forever in each direction. So what I need is a point, right? So I need a point that lives on this line, any point I can find. And then I need a direction vector. So I need some vector that points either out in this direction or this direction, doesn't matter. So let's start with the point. How can we get the point? Well, we just need to find, right? We need to find a point, an x, a y, and a z, which satisfies both of these equations at the same time. So what we can do is we can just kind of pick something and guess. Because we have two equations and we have 3 variables, so one of these variables is kind of free. We can let it be whatever we want. So I'm going to let z be 0. I'm going to see if I let this z be 0, if I can find x and y. So if z is 0, let's rewrite the equations. X plus 2y equals 1, and then over here x minus y equals 1. So is it possible for me to solve this system of linear equations? So depending on how you feel about this and what you've seen in college algebra or wherever, there's different ways to solve these. What I'm going to do is I'm going to solve by elimination. So I'm going to multiply the bottom equation by -1, and then I'm going to add these 2 rows together. So if I add down, see, this is going to make my x's go away. X goes away. I get 3y equals 0, which means y is 0. Okay, so if y is 0, so what I've done is I've let z be 0. When that happens, that means y has to be 0. And if y is 0, I can go back to any of these equations. So I'll just go right to this equation. I'll replace y with 0. I get x minus 0 equals 1, which means x is 1. So according to what I've done here, the point 1, 0, 0 should live on both planes. So let's just check it. If I plug in 1, 0, 0, is that true? Yes. I plug in 1, 0, 0, is that true? Yes. So that point lives on the line of intersection of those two planes. So I'm starting to get the things I need. From here I can rewrite R naught is the vector 1, 0, 0. So I'm converting that point to a vector. And now all I need is the direction. So I need the red part, right? So remember from class that if we have two planes that intersect, then I can imagine the normals for each of these planes are perpendicular to the planes, right? So this plane has a normal vector, this plane has a normal vector, and if I take those two normal vectors and I cross them, right, so the normal here and the normal here, if I cross those two, I'll have a vector that's going to stick out and it will actually run parallel to the line of intersection. So what I need to do to find V is I need to take the cross product of the two normal vectors. So I'll say normal 1 and normal 2. So this is the first plane. What is the normal vector for this plane? Well, you just look at the coefficients. The normal for the first plane is 1, 2, 3. And then the normal vector for this plane, which I'll call N2, are the coefficients here, 1, negative 1, and 1. So if I cross these two vectors, so normal 1 crossed with normal 2, that'll be our V. Let me actually write these down vertically so it'll be a little easier for me to do. And yeah, I know what I'm doing here. Okay, so this V that we're getting, cover up the I, right? And I do 2, and then take away negative 3, which is same as adding 3, so 2 plus 3 is 5. And then I cover up the middle. I've got 1, take away 3 is negative 2, but then subtract it, so 2. And then cover up the last part. We've got negative 1, take away 2 is negative 3. So that should be the direction vector that we use for our line. So we're ready. Put it together. R of t equals R naught plus TV, which is R naught was 1, 0, 0, plus t times our direction vector, 5, 2, negative 3. And then what we'll do is I'll just put it all together right now. So we have 1 plus 5t, 2t, negative 3t. T is a real number. This should draw the line that is the intersection of those two planes. What number was this? 10? All right, now the parametric equations are here. So there's your parametric equations. Let me solve these. If I take this, solve it for t, I get x minus 1 over 5 equals t. I did this one a little different. Instead of writing x minus 1 equals 5t, and then dividing by 5 and putting 1/5 x minus 1/5, I just left the 5 on the bottom of everything. The book does that a lot. Over here, y over 2 is t, and over here, negative z over 3 is t. So if you set this equal to this equal to this, there's your symmetric equation. All right, that's it for 10. How am I doing on time here? 45, so let's see what else I have to do. Okay. Let's do 12. Says, is the line through these points. So let me write down the points. You have a line. It goes through the point -2, 4, 0, and the point 1, 1, 1. And then we have another line, and it goes through the points 2, 3, 4, and 3, -1, -8. Let me just make sure I copy that down right. Okay, so we have two lines here, right? And the first line goes through these 2 points. So let's just make these points up. I don't feel like drawing it accurately. So we have 2 points, right? We'll call this L1. Okay, so it continues forever. And then we have another line which goes through these 2 points. I don't know where they are, so I'm just going to kind of make them up. I don't know. There we go. And it continues forever. Right? And the question is the line through these 2 points, L1, here's L2. So this is L1 here through those two, and this is L2. Is the line through these 2 points perpendicular to the line through these 2 points? So how do we determine this? Well, one thing we could do is use the fact that if we take 2 vectors, right, we can tell if they're perpendicular to each other pretty easily. All we do is take the dot product. If the dot product is 0, then they're perpendicular. If the dot product is not 0, then they're not perpendicular. So I need to know what the directions of these lines are. If I come in here and I say, all right, let me find the direction of this line, I can just make a vector that connects those 2 points. I'll call that V1, or sorry, let's make it V2. That's the direction of the second line. And if I do the vector here to here, I call that V1, that's the direction of that line. And if I just bring these two together and take the dot product, I'll know whether or not they're perpendicular. So how do we get V1 and V2? This is pretty straightforward. So for L1 to find V1, we just need a vector connecting these 2 points. So I'm going to go from here to here. So 1 take away -2 is 3. 1 take away 4 is -3. 1 take away 0 is 1. Now the second direction vector connects these two. So 3 minus 2 is 1. -1 minus 3 is -4. And -8 minus 4 is -12. Now I'm going to check what's V1 dotted with V2. Well, that's 3 times 1 is 3, plus -3 times -4 is positive 12. And then -1 minus 12, that's -1 times, 1 times -12 is -12. These cancel, we just get 3 there, but that is not 0. So therefore, they are not perpendicular to one another. So that was 12. Let's look at 13. All right, so number 13 part A seems pretty simple. Part B is the more interesting part. All right, so for 13, they give you they say find the symmetric equations for the line through the point 1, -5, 6 and is parallel to the vector -1, 2, -3. So find the symmetric equations for this. Well, that's pretty easy because in order to find the vector equation of a line, we need a point and a direction, which we have right here. So r of t should be equal to the vector 1, -5, 6 plus t times the direction of the line. So since it's parallel to that vector, we're just going to use that vector itself as the direction. So 2, -3, which is 1 minus t, -5 plus 2t, and 6 minus 3t. So that's the vector equation. We want the symmetric equation, so we have to now go to the parametric equations. X is 1 minus t, y is -5 plus 2t, and z is 6 minus 3t. And then finally, solving each of these for t, you get, what is it, 1 minus x is t on that one. Solve this for t, you get y plus 5 over 2 is t. And then on this one, you get z minus 6 over -3 is t. So the symmetric equations are 1 minus x equals y plus 5 over 2, which equals z minus 6 over -3. So that's what they wanted. For the first part, that's only 13, part A. And now what we need is to answer part B, which is more interesting. Part B says, find the points in which the required line from part A intersects the coordinate planes. So there's a line sitting out here in three-dimensional space, and we're trying to figure out where this line hits the coordinate planes. So imagine we have our standard x, y, z, right? And we've got some line arbitrarily drawn through here in three-dimensional space. And it hits the ground, the xy plane somewhere. I'm just going to kind of guess here. It hits the ground there. It hits the yz plane somewhere. And then it hits this wall, the xz plane somewhere. I don't know. We need to find out where those points are. So the question they're asking is, when does this line hit the xy plane? When does it hit the yz plane? When does it hit the xz plane? Or at what point does it hit? So let's start with trying to figure out, I think I'll erase this. So I want to know, when does this r of t hit or intersect? Let's start with the xy plane. Well, the xy plane is another way of saying all the points where z are 0, right? When you're on the xy plane, z is 0. So what that tells me is that when this line right here hits the xy plane, I know the z value, the z component of the vector must be 0. I know that this must be 0. So this implies that the 6 minus 3t must be equal to 0, right? The z is 0, so that must be true, which means that 6 equals 3t, which means that t must equal 2. So at t equals 2 is where it happens, or is when it happens. So what I need to do is come back over to this and figure out where I am at 2. So plug 2 into the whole thing. And I get 1 minus 2 is negative 1. Negative 5 plus 2 times 2 is 4, so negative 5 plus 4 is negative 1. And then here we already know that when I plug 2 in, I get 0. And now I convert that to a point, and that's going to be the point negative 1, 0. So that at that point is where my line would punch through the xy plane. Now we want to do the same thing again, but now we want to do it for the y. Let's do the yz plane next. Okay, for the yz plane, what's the restriction? If we're on the yz plane, x must be 0 this time. And then we go back and we say, all right, well, if x must be 0, then the x component right here on our line must be 0. So 1 minus t must be 0, which means t must be equal to 1. And so we come back and we say, all right, well, let's just plug 1 in and see where we are. So when we plug in 1, we get 0. We kind of knew that. Plug in 1 here, we get negative 3. And then we plug in 1 here and we get 3. Convert that to a point, and we get 0, negative 3, 3. So our line should punch through the yz plane at that point, 0, negative 3, 3. And then finally, if we want to find out where it goes through the xz plane, we know in that case y must be 0. And that means that negative 5 plus 2t must be 0. And then that means that t must be 5 halves. And then we plug 5 halves in. And that won't be as fun, but let's do it. 1 take away 5 halves is negative 3 halves. We already know what happens to the y component, 0. 6 minus 3 times 5 halves. This is not fun. This is 15 halves, so 6 minus 15 halves. That's the same as 12 halves. So negative 3 halves, right in here. Negative 3 halves. That should, oh, and then convert it to a point. Negative 3 halves, 0, negative 3 halves. That point. Let me double check this. This is number 13. Yeah, looks good. Okay, I think that's enough on time here for this one. Where's my little sheet? Where'd it go? Oh, there it is. So I've done 13. I still have some more to go here, but I gotta stop for right now. Hey, welcome back. Do some videos here for the homework for 10.5, continuing 10.5. I had finished up number 13. I was moving on to 15. So let's take a look at this. All right. Find the vector equation for the line segment connecting the, from the point 2, negative 1, 4 to the point 4, 6, 1. So we want the vector equation that's going to connect this point to this point. And the important thing is that we want the segment, not the complete line itself. So if I were to, sketch this thing, oops, 2, 1, 2, negative 1, 4, point something like that, then maybe like 4, 6 would be maybe down here, and then 1. So we've got these 2 points. I'll call it, point A and point B. So we want to look at the line segment that connects these two. We do not want to continue and extend that line forever. All that means that we're going to need to restrict what t is. All right, so we're not going to let t be all real numbers. If we do that, it'll draw the whole line. And so what we do is we need to find a point on the line and a direction. Well, we have 2 points to choose from. And so if you're going to use the method that I show in class, what you do is you always pick the point you're going to start from as your R naught. So we're going to choose R naught, that vector, to be the starting point converted to a vector. And that's going to, I'll try and draw here what's happening. From the origin to that point right there, that's R naught. And now what I need is a direction vector. And the direction vector I use is the vector that connects point A to point B, right? This is point A. This is point B. And that vector is going to be my direction vector V. So V is the vector connecting these 2 points, right? This point to this point. So I'm going to go 4, take away 2, that's 2. I'm going to go 6, take away -1, that's 7. And I'm going to go 1, take away 4, that's -3. So that's my direction vector V. And so I come up with my formula. My formula will be R of t equals R naught plus t times v, which is 2, 7, -3. Now, again, the key to this is that if t is all real numbers, then it's going to draw the entire line, not just the segment. But if you do it the way I showed you here, you start at this point, you're going to this point, so you convert this to the vector, you use the vector from A to B as your v, then you will always just restrict t between 0 and 1. Now, you could also write that t is an element of the closed interval 0, 1. Either way. And so what happens is if t is 0, right, then this is all gone, and you're just pointed out towards this point right here, right? You're the red vector, which points you here. So you're at the start. And then if t is 1, let's just say t is 1, which would be the extreme other end, then you add these two. This will be 1 times this, which is just this vector. You add these two together. 2 plus 2 is 4, and that would give you this. -1 plus 7 is 6, that would give you this. And 4 take away 3 would be 1, and you'd be here. So then, at t is equal to 1, you're actually from the origin to this point. And so you take some t that's in the middle, like let's say you take t is 1/2. So what you're going to do is you're going to take this vector, you're going to add half of this vector. So this vector goes from here to here, then you're going to add to that half of the green one, which will take you halfway down the green one. And so the resultant vector, right, starts at the origin, goes here, then goes halfway, is from the origin to this point on the line. Ooh, line segment right there. So you can kind of see that, if t was 0, you're here. If t is 1, you're here. If t is 1/2, you're here. So if t is 1/4, you're going to be here. If t is 3/4, you're going to be here. And if t is everything between 0 and 1, it's going to draw the entire segment, but nothing further. All right, that's 15. Oh, you know what? I could put these together. I never did that. You could get a final answer here. R of t equals, just put these two together. So 2 plus 2t, -1 plus 7t, and 4 minus 3t. And of course, t is between 0 and 1. do we do it now? 17? Determine whether the lines L1 and L2 are parallel, skew, or intersecting. So we have two lines. L1 is given by the parametric equations x equals 3 plus 2t, y is equal to 4 minus t, z is equal to 1 plus 3t. L2 is x is 1 plus 4s, y equals 3 minus 2s, and z is 4 plus 5s. So they're using the variable s in the second line as opposed to t in the first line. So that's just because you want to be able to draw this one, letting t be all real numbers. That'll draw the entire line. And then this one, you could use t again, but we're going to use s because there's nothing that says you have to draw both these lines at the same time. So if I plug in t as 1 here, right, and just draw whatever vector that draws or point in three-dimensional space, then there's nothing that says that I have to draw this point at 1 also, s is 1. I don't have to do that at the exact same time. So these two lines aren't connected by the same variable of t. So that's why we use a different variable, s. All right, so are they parallel, skew, or intersecting? All right, so are they parallel, skew, or intersecting? So here's what they want to know. Visually, this is what we're looking at. You've got two lines in three-dimensional space here. I'm trying to figure out if these lines are parallel, which means they would point in the same direction. Are they skew, which means that they aren't parallel and they don't hit each other? Or are they intersecting? So do they actually hit each other, right? Cross somewhere. All right, so what should we check first? Why don't we check for the parallel? So to be parallel means that these two lines have to point in the same direction. So why don't I try and find the direction vectors for each of these lines? Remember that each of these lines, you can find the direction v. I'll call it v1, and for this one I can find v2, so which way they're pointing. And from what we've done in the past, we know that the direction vector comes from the coefficients of the variable in the parametric equation. So the 2 here, there's a -1, and then in front of this t we've got a +3. So what I can say is that the direction of line 1 is the vector 2, -1, 3. I can do the same thing for L2. I can find its direction looking at the coefficient of the variable, so 4, -2, and 5. So the direction of the second line is 4, -2, and 5. So the question is, are these parallel? So we go back to, how do you determine if two vectors are parallel? Well, we want to see, is V1 some multiple of V2, right? So is there a number that I can multiply to get from this vector to this vector? So can I scale this vector in a way that it creates this? Well, the only way I'm going to be able to do that is if I can get the 2 to become a 4. So how would I make the 2 a 4? I would actually have to double, right? So also, I could have written this instead. V2 2 is some multiple of V1. It doesn't matter, either one of these. I just need to show either one of these is true. So I notice that if I take V1 and I multiply it by 2, I'm going to get a 4 here. So I'm kind of saying this. The question is V2, is it 2 times V1? Well, the first component's okay, right? If I take 2 times V1, I get 2, and then, I'm sorry, I get 4. But then the next component, I multiply here, I get -2, and then when I multiply that by 2, I get 6. And you can see here that if I do this, I do not get V2. Yeah, the first component's the same, but these two are, well, this component, sorry, is also the same. That works. But the third component doesn't match. And so there's no way I'm ever going to be able to scale V1 by a number and get V2. It's just not going to happen. So they are not parallel. Let me see. Are they skew? Well, that's actually very difficult to show because what we need to do is show that the vectors don't hit each other. Like there's never a point that they hit together. So what I'm going to do to determine if they're skew is I'm going to ask myself, are they intersecting? So do these actually share a point? Do they actually hit at some point? So remember that for different values of t, right, I draw different points. They're really vectors, but they correspond to points on the line. So for different values of t, I draw all these different points. And for different values of s, I draw all those points on the second line. So the question for the intersecting is this. Does there exist a t and an s such that the first line, L1 at t, is the same as L2 at s. So is there some point in time, t, right, or some value of t, that when I plug it into L1, it matches with L2 for some value of s? Now, I think I'm going to write this a different way, okay? So what I'm going to do is I'm going to rewrite L1 in a vector form, a vector function. So I'm going to call R1 of t, which is L1, so this is R1, is going to be this written in its vector form. So 3 plus 2t, 4 minus t, 1 plus 3t. And then I'm going to write the vector form of the second line, which I'll call R2 of not t, of s, equals 1 plus 4s, 3 minus 2s, and then 4 plus 5s. So that question I was just asking is saying this. Is there some value of t that when I plug it in here, I can get it to match with this vector for some value of s? So I'm trying to find a t and an s that I plug into both of these and I get these things to match. Well, let's think about what that means, all right? I'm going to need these to match, I'm going to need these to match, and I'm going to need these to match. So that means I have 3 different equations that have to be true. I have to have 3 plus 2t must equal 1 plus 4s. I need that to be true. I need 4 minus t to be equal to 3 minus 2s. And lastly, I need 1 plus 3t to be equal to 4 plus 5s. And so what I have is a system of equations here. Yeah, that's good enough. Well, maybe not. That's not a very good brace. Okay, so I have a system of equations. And I have 3 equations, but I only have 2 unknown variables. So I should be able to get this with relative ease. what I will do is I will rewrite just the first two equations. I'm going to bring all my t's and s's to one side and all numbers to the other side. So 2t I'm going to leave here. I'm going to bring the 4s to this side, so minus 4s equals, and then I had a 1 here, a 3 here, I'm going to subtract, so I'm going to get negative 2 here. So that's the first equation rewritten. Second equation is negative t, and then I'm going to bring this over, the negative 2s becomes plus 2s. And then I have a 3 over here, I'm going to subtract 4, I get negative 1. So that's the first thing I have to be true, right? This has to be true and this has to be true, which means these two have to be true. I'm going to worry about this one in a second. So now for this simple two equations, two unknowns, I can use elimination, I can use substitution, depending on what you've done in the past. I'm just going to do elimination, and what I'm going to do elimination is I'm going to try and kill off the t's. So I'm going to multiply this equation by 2 and then rewrite the system. So I have 2t minus 4s equals negative 2, and then here I get negative 2t, and then 4s equals positive 2. And this is strange. When I add down, I get 0 equals 0. Well, what does that mean? What does that mean? 0 equals 0. If you recall back from solving systems of equations back in college algebra, when you get something like this, that actually means that there's an infinite number of solutions. If I plug in a t for this, there's going to be an s that works, and the same t and the same s will work here. So there's an infinite number of pairs that are going to work here. So I don't really have a lot of information from this. So what I'm going to do now is I'm going to move on to this right here and work with, let's say, the second and third equation. Now let's try and rewrite this again. You know what? I don't need this anymore. So let's take this equation, the second one, which we already had simplified over there, brought everything over. Negative t plus 2s equals negative 1. And then I'm going to do the same thing for this one. So 3t, and then I'm going to bring over the 5s, so minus 5s equals, and then I'm going to bring the 1 over here, so 3. And let me do the same thing. I'm going to try and solve that. So I'm going to eliminate the t's again. So I'm going to have to multiply the top one by 3, top equation. I get a new system, negative 3t. I get positive 6s equals, let's see, negative 3. And then over here, nothing changed, equals 3. So now we add straight down, we get 0. Here we get s equals 0. Now that's some information. It's saying in order for these to be true, right? For these to be true, I need s to be 0. So if s is 0, now I go back and I can plug in for either one of these, s is 0. So let's take that first equation up there. Negative t plus 2 times 0 must equal negative 1, which means that negative t must equal negative 1, which means that t must be 1. So this is what I think is going to work. I think t is 1 and s is 0 should make these two lines intersect. However, we need to check it. Okay? So I had erased them, so let me put them back up here. Which number was this? This was 17, right? So remember I'd said R1 of t was the vector 3 plus 2t, 4 minus t, and 1 plus 3t. And R2 of s was 1 plus 4s and 3 minus 2s and 4 plus 5s. Okay, so what I'm saying is I believe that t is equal to 1 and s is equal to 0 will work. And remember, these equations came from these last two, right? We were working with this one, and then we simplified and got to these two. So let me just check these two should work. If I let t be 1 and s be 0, what happens? So if t is 1, right here, I get 3. I'll just put it above there. I would get 3 here. If t is 1 here, I'm going to get 4. Okay. Now let's let s be 0. If s is 0 right here, I get 3. And if I let s be 0 here, I get 4. So look, they're matching. The question still remains, though, what about the first component? I know that t is 1 and s is 0 will force these two to be the same. That's the only way I can do it. Here, though, if I try t is 1 and s is 0, if t is 1, what happens here? We get 5. And if s is 0, I get 1. And these two don't match. So I went about this and I tried to find, I'm trying to recap here. I'm trying to figure out what makes these match, and these match. When I tried to figure out when these two matched, I figured there was a bunch of different values I could do. There was an infinite number of solutions. So that wasn't enough for me to nail anything down. So then I went with these two. When I went with these two, to make those match, I have to have this happen. But if that's what has to happen to make these two match, then this also needs to work for this, but it doesn't. Therefore, these two lines cannot possibly intersect. I can't find a t and an s that works for both, or works for all of these. So they don't intersect. And if they don't intersect, then it's a skew. It's a skew line. Okay. What's next? I would encourage you to try and do like number 18 on your own. 18, they turn out to be parallel. See, 19, they're also parallel. Oh, sorry, no. 19, they do intersect. 20 is skew. So maybe I should do 19. What do you think? Should I do 19? No, I'm not. What happens is that, let's say on this last problem, I think we had, what, 3 and 4 matched up in the second equations. In number 19, if you work through this and you get your s and your t, and you check these and they matched up 3 and 4, and let's just say the first one when we plugged in the two values for s and t, that these match too. Let's say this was 7 and 7. Then you would say they intersect, and you would actually say they intersect at the point 7, 3, 4. Okay, whatever these components were, that's the point that they hit each other. You would not put as your answer s is 0 and t is 1, because you would want to know where they intersect. So you would say the lines intersect at the point 7, 3, 4. All right. And of course, if they're parallel lines, then in that first step when we were checking the direction vectors, they would have been parallel, so they would have been scalar multiples. So like on number 18, I said are parallel. Okay, what's next? 21. All right, so here's where we start getting some good stuff. 21. All right, the instructions here are to find an equation of the plane. So I have a plane that's through the point -1, 1/2, 3. And then the normal vector is given to me as I, 4j, k. So 1, 4, 1. go on my notes real quick and make sure I use the same formula that I used in class. So equations of planes. So this is note 10.5.14. Remembering that for a plane, the equation of a plane is given by A, x minus x naught plus b times y minus y naught plus c, z minus z naught equals 0. Where ABC, these numbers ABC, are the components of the normal vector, and x naught, y naught, z naught is a point on the plane. So what we know basically from this formula is that if someone gives us a vector that is parallel to the normal, so any normal vector to the plane, and a point on the plane, we can find the equation. And in this example, or in this problem, they give us exactly what we need. They give us a point, and they give us the normal vector. So all we have to do is plug into this. You know, this is A, this is B, this is C, this is x naught, y naught, z naught, and we just plug in. So I'm going to do that right now, and then we're going to clean it up and have a nice answer. All right. So A for us is 1. So 1, x minus negative 1 is plus 1. Plus, let's see, b is 4, and then y, let's see, minus a half, plus c, which is 1, and then z minus z naught, which is 3, equals 0. So that is the equation of the plane, but we're gonna distribute and make it look a little different. So passing things through here, distributing. There we go. And now what I'll do is I'll get all my letters, variables on one side, x plus 4y plus z equals, and then on the other side, the numbers. So I have 1, take away 2 is negative 1, minus 3 is negative 4, but then we move it to the other side, so 4. That is the equation of the plane that goes through that point and has a normal vector of 1, 4, 1. All right, let's look at number 22. That problem was about as easy as they get. Find the equation of the plane through the point. So they give you a point 2, 0, 1. And they tell you that it is perpendicular to the line x equals 3t, y equals 2 minus t, and z equals 3 plus 4t. So let me try and illustrate this. Give me just a second. I'm going to go grab something. Okay, I went to go find a plane. So here's a nice rigid plane. I'm trying to find the equation of this plane. And what I know is that it goes through that point. So remember, for a plane we need a point and a normal vector. So I have a point, so that's good. The only thing left is to find a vector that runs out of the plane, so perpendicular to the plane. So any vector that runs perpendicular to this plane will work. And they give us that this plane needs to be perpendicular to this line. So now we've got some line that they're giving us that's sitting out there, right? And we know that our plane has to be perpendicular to this. So if we were to move this vector towards our plane, our plane would have to run in there at a 90-degree angle. So notice that the direction, right, the direction vector of this line would qualify as a normal for the plane. So all we have to do is identify what the direction of this line is. So if we look at this as a line, what is the direction vector, which we call v, of that line? So remember, all we do is we pull the coefficients off the t's. So 3 here, -1, and then here 4. So I know that the direction vector of that line is the vector 3, -1, 4. And then, because my normal needs to be pointed in the same direction as that, I can just say, let's let the normal be that same vector. And of course, that'll point in the same direction. It's the same vector. Now, you could double it. You know, you could say 6, -2, 8. You could be crazy and divide by 2. You could scale it. It doesn't matter, as long as it's pointed in the same direction. So at this point, I just go straight to the formula. A, x minus x naught, plus b, y minus y naught, plus c, z minus z naught equals 0. Here's my x naught, y naught, z naught. And this direction vector is my normal vector, so that's ABC. So I'm going to get 3, and then x minus 2, minus 1, and then y minus 0, and then plus, let's see, c, which is 4, and then z minus 1, right, equals 0. And then I'll just clean it up. So distributing through here, we get 3x minus 6. Distribute -1 through here, we get -y, and then the 0 doesn't matter. And then plus 4z, and then minus 4 equals 0. And get all the variables on one side, all constants to the other side. -6, -4 is -10, take it to the other side, 10. This is the equation of the plane that passes through that point and is perpendicular to the line that was given to us. So that's number, what, 22? Okay. Number 23. Same thing. Find the equation of the plane through the point. Wow, they keep on giving us a point. This is, they're making it easy. They give us a point, what do we need? That's the only thing we need. Direction vector, right? And I need to be parallel to the plane, and then they give me a plane equation. 5x minus y minus z equals 6. Wow, okay. So they give you a point sitting out here in space. Boom, there it is, right? They give you a plane. Boom, sitting right here out in space. Right, that's what they give you. And you're trying to find the equation of the plane that goes through this point that's parallel to this plane. So imagine just moving this plane up, right? Don't tilt it, just bring it up, slide it over underneath, and put it where that point's on that plane now, right? Then do you agree that the normal vector on this plane, right, when we slide this up, is also the same as the normal vector on the plane we're looking for? So we actually have a point that we need to have, right, for the equation. And then we need the direction vector, but the direction vector, the normal vector for our plane, is exactly the same as the normal vector for this plane. And so all you have to do is identify what the normal vector is for this plane, and that's super easy to do. All you do is peel off the coefficients of x, y, and z. That's it. The numbers in front of x, y, and z will be the normal vector of that plane. So the normal vector of this plane is 5, -1, -1. And well, hell, we're going to use that as our normal vector also. So let me do this kind of quick. I'm going to use the formula, right? This is A, B, and C. And then this is our x naught, y naught, z naught. And I'm just going to do it all together at one time. So 5, and then x minus x naught plus b, but it's -1, and then y minus y naught, but that's +1, and then c, which is -1, and then z minus z naught, but that's z plus 1, so that's equals 0. Distributing through, 5x minus 5 minus y minus 1 minus z minus 1 equals 0. And we should get 5x minus y minus z equals, let's see, this is -6, -7, take it to the other side, so 7. This should be the equation of the plane. And what you'll recognize when you look at this is that if we go back up to this one, this was 5x minus y minus z. That was given to us in the problem. You'll notice that these two equations are very similar. Well, they should be. They should be pointing in the same direction, which they are. 5, -1, -1, right? Same direction vector. The only difference is the constant on the other side, and that's really what had the effect of moving it. And it moved it exactly so that it would pass through that point. So should we check it? Let's just check. Does this point live on that plane? Let's just plug in 1, -1, -1. So what happens if we plug in 1 here? We get 5, -1 into this, negative is plus 1, and if we plug in -1 in there, we get plus 1 again. And is that 7? Well, 5 plus 2 is 7. That's checked. So yeah, that point lives on that plane. Cool. All right, 24. So find the equation of the plane that contains, the plane contains the line, and they give it to you in parametric form. X equals 1 plus t, y equals 2 minus t, z equals, come on, where are you? 4 minus 3t. And is parallel to the plane 5x plus 2y plus z equals 1. All right. So in this problem, we're asked to find the equation of the plane that contains this line and is parallel to that plane. So let me show this to you again. So we have a line sitting out here in space. Here it is. And we have a plane, okay, that's given to us. And our plane that we're trying to find contains that line. So let's just say the line that we have, right, goes into our plane. But see, there's all sorts of planes that would contain this line. If I rotate this around, the direction of the line doesn't change. So there's an infinite number of planes that contain this line. But what we want is to find the equation of the plane that has this line in it, but runs parallel to some other plane that's given to us. So there's another plane sitting out here, in whatever direction it is. We need to kind of rotate this plane around this line to make these two parallel. I hope that makes sense. But we can get caught into, trying to understand it, visually, and that can sometimes be hard to do. Let's just get down to what it is we need for the equation of a plane. For the equation of a plane, you need two things. You need a point, you need a normal vector, right? That's what you need. All right, so let's discuss the normal vector, because this problem is very similar to the last one. We have to be parallel to a plane, right? To be parallel to this plane means that I can use the normal vector of this plane as my normal vector for the plane I'm looking for. So why don't I let my normal vector be the same as the direction vector of this plane, which is 5, 2, 1. I'm getting that from the coefficients on the x, y, and z. There's a 1 there, right? So good, I've already got that. All I need now is a point on the plane. If I can find the point, I'm done. Well, if this line, right, if that entire line is on the plane, then every point on this line is on our plane. And I just need one of them. So how can I get a point on this line? Just let t be anything you want it to be. Just get a point off this line. Let t be, let's say 0. I like 0 because it's easy to plug in. If t is 0, where are you going to be? You're going to be at the point 1, 2, 4. So surely if that point lives on this line, then and our plane contains the entire line, then that point lives on our plane. So we have a point and we have a direction vector. That's all we need. So someone else could have come in here and done this problem, and they could have said, hey, I'm going to let t be 1, and they would have a different point. Is that going to change our answer? I'll show you it's not. Okay? So let's do this. I'm going to use this point and this direction vector. So using the formula, you get 5, that's A, x minus x naught, plus b, y minus y naught, and then plus c, which is 1, and then z minus z naught equals 0. So there's a, b, c, x naught, y naught, z naught. There it is. Let's distribute through. 5x minus 5 plus 2y minus 4 plus z minus 4 equals 0. So we wind up with an answer of 5x plus 2y plus z equals, look, these are the same, but this number is going to be different, watch. Negative 9 and then negative 13, bring it to the other side, positive 13. That is the equation of the plane that is parallel to this plane and contains the entire line. It's kind of amazing that that entire line is in there, huh? Should we check first that this point does live there? Plug in 1, 2, 4. So if I plug in 1, 2, 4, plug in 1, we get 5, 2 in here, we get 4, plug in 4 in there, we get 9 plus 4 is 13, that checks. And I said it didn't matter what point I picked, so I bet you any other point on this line is going to live there too. Should we check another one? Let's see. If I let t be 1, where are we going to be? So 1 plus 1 is 2, 2 minus 1 is 1, and then 4, ooh, if we plug in 1 here, we just get 1. So what would happen if we plug that point into this? So 2, so 5 times 2 is 10, plus 1, let's see, 1 times 2 is 2, plus z is 1. Oh, wow, it's 13? Huh, interesting. Every single point on this line lives in there, lives on that plane. That's very cool. So what if you would have come in here and you would have said, you wouldn't have done t is 0, right? And you would have been trying to come up with this equation, and you would have used 2, 1, 1 instead. So this would have changed, right? Let's see the difference. See if we get a different answer. So if I plug in here 2, plug in here 1 and 1, and distribute 5x minus 10 plus 2y minus 2 plus z minus 1, then I get, look, 5x plus 2y plus z, that's the same. Negative 10 minus 2 minus 1, that's negative 13, still 13. It works. It's the same. Amazing. We're done. Starting to get excited. I like this stuff. All right, next one. 25. Ooh, find the equation of the plane through 3 points. Find the equation of the plane through 3 points. So if someone gives you 3 points and asks you for the equation of the plane through those, can you find it? I feel like I've got something on my back. What the hell is that? It's weird. Okay, I'm going to draw this. Because we have 3 points, it'll be easy for me to draw the plane. 0, 1, 1. So there's 1 point. 1, 0, 1, which is this point, and then 1, 1, 1, 1, 0, which is this point, and connect these together like this. Now imagine that triangle extended out in every direction, and what you'll have is a plane. So what's the equation of that plane? Well, here's how we're going to do this. You know what? Let me go get something else. See how long my video is. All right, this will be the last example I can do on this video. All right, so here's that plane, right? So it's those 3 points connected here. Like this. So we got that plane sitting there, right? Creates this plane. I'm trying to find the equation of this plane. So what do we need for the equation of a plane? A point and a direction, a normal vector. Well, I have 3 points to choose from, so I'm just going to use this as my point. I could use any one of them. And then all I need now is a normal, right? What's the normal vector? Well, if we look at the vector that's going to point out of this plane, right? It's going to be perpendicular to this plane. Then what I could do to get that normal vector is I could look at creating 2 vectors on my sheet of paper. So the vector that would go from this point to this point, put an arrow on it because it's a vector. I could take this, which goes here to here. So let me label these. This is A, which was this point. B was, oh sorry, no. A was, what was A? 0. Oh shit, hold on. 0, crap, my picture's wrong. Start this over. I think my picture was wrong. 0, nowhere on the X, Y, 1, Z1. And then 1, don't go left to right, go up 1. And then 1, 1 out this way like this. Creates that triangle. I don't know why I screwed that up. Okay, so look, here's what I'll do. Sorry about that. Doesn't matter. I've got 3 points. I'm going to label them now. 1, 1. This is A, so that's A. B is 1, 0, 1, so this is B. And then C is this one right here. C. Okay. So if I take these 3 points in space, they make a plane. I can, again, for the equation, I need a point, so I'm just going to use that first one, A. And then what I did is I came in here and I'm going to create a vector, a couple of them. A, here's B, here's C. So how about I do a vector like this? I'll stick with kind of the same as what I was doing before. From here to here, vector, and from here to here, a vector. And I'm trying to find this normal that's pointed out. So what I do is I take these 2 vectors, right, and I cross product them. And when I cross product these vectors, right-hand rule, right, this thing will stick out. Or it could be possibly pointing out the bottom, but it doesn't matter. This is a normal vector. And so I just need to cross those 2 vectors. So I'm going to try and find this normal vector. I'm going to define it to be the vector that goes from B to A crossed with the vector that goes from B to C. If I cross those, I'm guaranteed a vector that's perpendicular to both, so it's going to be perpendicular to the plane. Hope that makes sense. Again, I apologize about my crappy drawing to start. So I need to actually come up with some vectors here. So what is the vector that goes from B to A? So from B to A, so I'm going from here to here. So I'm going to take 0 and subtract 1, negative 1. I'm going to take 1 and subtract 0, so that's 1. And then I'm going to take 1 and subtract 1, which gives me 0. So that's the vector going from B to A. Now the vector from B to C, I'm going to do 1, take away 1, which is 0. I'm going to go 1, take away 0, which is 1. And I'm going to go 0 and take away 1, which is negative 1. And now I need to cross those two. So to cross those two, I'm going to write them vertically. I'll put the answer right here. So I'm going to get the I component first, so I cover it up. I go 1 times negative, so that's negative 1 minus 0, so just negative 1. And then I cover up this one. Negative 1 times negative 1 is 1. Then minus 0, so I have 1, but then I'm going to subtract it because it's the j. So minus 1. And then I cover up the k, and I get negative 1, take away 0, so just negative 1. So that's my direction. That's my normal vector for my plane. Okay, this is n. And now I just use the plane formula. I think I can squeeze it in. Well, I'll just put it right here. I need a point, which I've got. I need my direction, my normal vector. So that's your ABC. This is your x naught, y naught, z naught. So I should have negative 1, x minus 0, minus 1, y minus 1, and then minus 1 times z minus 1 again, equals 0. And then at this point, I just distribute through, get negative x minus y plus 1 minus z plus 1 equals 0. And I need all my variables on one side. I could leave them on the left, but they're all negative, so why don't I move them to the right? The left side will be 2. Then I get x plus y plus z. And that's the same as writing it the other way, x plus y plus z equals 2. And that's it. That's number 25. And that's good. Okay, I'm going to stop this video. These videos can only be about an hour long, and then it breaks it into 2 videos, so that's why I try and do just 1 hour. What am I doing? So I'm trying to go all the way through 32 on these. 26. Find the equation of the plane through the origin. So it's through the origin. That's this point. And the points 2, negative 4, 6. And 5, 1, 3. Well, hey, this is just like the previous problem. They give you 3 points. So you just A, B, C. And then just imagine these points out here. Doesn't matter where they are, A, B, C. So you'll create 2 vectors. Go A to C, A to B. Right, figure out what those are. Cross them. When you cross them, you'll get a normal vector coming out of this plane. So your normal vector will be AB cross AC. And then a point, of course, you can use any of those points. So probably use the point 0, 0, 0. I'm not going to do the math on that. I think you can handle that. It's just like the previous problem. Okay, I had a little technical problem there. Going to do number 27. So we have a plane that passes through a point, which, good, we have a point given to us. And it contains the line. So this is a point that's on the plane. And it contains the plane that we're looking for contains the line x equals 4 minus 2t, y equals 3 plus 5t, and z equals 7 plus 4t. All right, let me try and show you what's happening here. We have a plane that we're trying to figure out what it is, right? What the equation is. We're given a point that lives on the plane. So there's a point, this point lives on this plane. We also are told that this line, right, this plane contains this line. So that whole line lives on this flat sheet of paper also. So what's the equation of this? Well, to find the equation of the plane, we need two things, right? We need a point and we need a normal vector. The point we have, so we just need the normal vector, right? Well, the normal vector is any vector that's going to be popping out of this plane perpendicular to the plane. So what I'm going to do is going to be pretty clever. I'm going to try and figure out any point on this line. So I'm going to pick some point that lives on the line. I'm going to find it. That's going to be easy to do. I'm just going to plug in t as 0, and that should spit out a point. And then I'm going to create a vector that goes from here to here. Then I'm going to look at this line and I'm going to look at its direction vector. So its direction vector must be parallel to this line, so its direction vector be something like that. And notice that if I take these two vectors and I cross them, right, if I do the cross product, I should get a vector that is perpendicular to both. And since both these vectors lie on this plane, the cross product should be a normal vector, should stick out of my plane. So I've got to figure out what these two are and then cross them. So I'm going to try and draw that on the board. It won't look as good on the board because my board is already flat here. So I have a point. That's the point 6, 0, negative 2. I've got some line, and now I'm going to find another point on that line. So if I come over here to the line, I let t be 0, boom, boom, boom. I'm going to get, what, 437? 0.437. Now, I need a direction vector. Sorry, that's supposed to be like on that line. Direction vector of this line. And that I could use the v, the direction vector for this line, which comes from these numbers right here. So that v is equal to the vector negative 2, 5, and 4. All right? And now I will create this vector which goes from here to here. And that I can do just by taking the vector that goes from this point to this point. I go 6, take away 4. So this is the vector, let me call this vector u. This is the vector, 6 minus 4 is 2. 0, take away 3 is negative 3. Negative 2, take away 7 is negative 9. So if I take u and I cross it with v, it's going to pop me out a perpendicular vector to both. That vector is either going to stick out like this or it's going to stick in. So it's kind of like when I cross these, depending on the order I do it, it's either going to be sticking out of the plane or it's going to be perpendicular but sticking out the bottom like this. Doesn't matter, they're parallel. And normal vectors, doesn't matter which side it's pointing out. So the normal vector for my plane, right, is going to be the cross product of u and v. So the normal vector that I'm looking for is going to be, I'll do u cross v, which is u is 2, negative 3, negative 9, and cross that with v, which was the direction vector of the line, negative 2, 5, 4. So when we cross these, what we do is, we line them up vertically, and then we do our, covering things up. So this should be equal to, I'm going to do this, change it like this. So I'm doing that, crossing with that. So if I want to find the I component, right? The I component, I cover up I. And then I go, negative 3 times 4 is negative 12. Okay, so negative 12, and then I take away negative 45. So negative 12, and I take away negative 45. So that's same as negative 12 plus 45, which is going to be 33. Now I cover up the middle one. I get 2 times 4 is 8, and then I take away positive 18, right? So 8, take away positive 18 is going to be negative 10. Then I switch it to positive. And then I cover this up, I get 10, and then I take away positive 6, so that's going to be 4. Just check that, make sure I got that before I go any further. Yes, okay, so that's it. That's my normal vector. And that's all I need. I have a point in a normal vector. I just go into the formula now. Here's my A, my B, my C. And there's my x naught, y naught, z naught. So I'm going to have something like this. 33, x minus 6, plus 10, y minus 0. So that's just 10y. I'll write y minus 0. And then plus 4, and then z minus negative 2 is plus 2 equals 0. So 33x minus, what's that, 90 plus 18 is 108. And then plus 10y plus 4z plus 8 equals 0. So 33x plus 10y plus 4z equals, and then let's see this and this together, that's negative 100, and so bring it to the other side, 100. Looking like this is it. This is 27. 190, what the hell? What did I mess up? 410. What did I screw up? Oh. See, this is what I'm talking about. Like when it comes to arithmetic, my brain just does not want to work. I don't know. I think as I've gotten older, I don't know, my brain's just become more lazy. 33 times 6. So it's 180 plus 18. I said, I don't even know what I said, 100 plus 18? 90 plus 18? I don't even know. This should be 180 plus 8, so 198. That should be 198. I put 108. I hope you're just sitting there laughing at me right now. Okay, and then this side right here, this will become 190. I'm glad I have the answers there to double check because it's ridiculous arithmetic like that. Okay. Oh, I should mention that if you happen to have crossed these vectors the other way, v cross u, you're going to get the same result except all these will be negative. And the effect that that has over here is that everything changes. Negative, 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 and then this is negative also. So just FYI. Where are we? 28. I need to go back to elementary school and do my arithmetic again. 28. I may have mentioned this before, but it's a misconception that math people are really good at like calculations. Like I've never been a human calculator where I'm just like, 197 times 243 is blah, blah, blah. It's just, that doesn't mean you're a math person. Okay, what we're doing here, this means you're a math person. That's my opinion. The plane that passes through the point, so I'm still trying to find the equation of a plane that passes through this point, so I've given a point, great, and contains the line. So it contains the line, this is just like the previous problem. With the symmetric equations, x equals 2y equals 3z. So this is exactly like the previous problem. We have a point that lives on our plane, we have a line, so we're going to create this new vector and we're going to cross them, and just like the previous one. The only difficulty is maybe this right here, because we're given symmetric equations instead of parametric. So let me just remind you what this means. This means that x is t, that 2y is t, and that 3z is t. All right, so from here we can solve these for x, y, and z. This is x is t, this is y is 1/2 t, and this one is z is 1/3 t. So they're your parametric equations from your symmetric equations. And so when I have my point here, 1, -1, 1, and I have this line, I'm going to get my direction vector off of this, which we call v. I'm going to get a vector connecting these two, which we called u in the previous problem. I just need to find that point. And the point is any point that lives on this line, so just plug in a value for t. How about 0, right? 0, that's just 0, 0, 0. Hey, so the origin lives on this right here. And the direction vector v, that's equal to, what's the direction vector of this line? It's the numbers in front of the t, so 1, 1/2, and 1/3. Now I'm not going to want to cross that because that's got fractions. So instead of using this one, since it doesn't matter, it can be any vector on this line, why don't I just multiply this through by, let's say, a common denominator? So how about 6? This is the vector 6, 3, 2. Okay, so that is a direction vector, points in the same direction as this one. I may as well use that. It has nicer numbers. And I've gone so far on this problem, I may as well finish it, I guess. What is u going to be? U is going to be the vector from here to here. Well, that's all these minus 0, so that's just 1, -1, 1. All right. So I'm going to say that the normal I'm going to use for my plane here is going to be the v, which is this vector, 6, 3, 2. And I'm going to cross it with this vector, so I'm going to do it vertically. Cross it with 1, -1, 1. And that will be equal to, let me take my time here. I'm going to cover this up. This is 3. Take away -2, that's the same as 3 plus 2, that's 5. And then cover up the middle, right? 6 take away 2 is 4, but then subtract it, so -4. And then cover up this one. -6 take away 3 is -9. And so what I should have here is hey, how's it going? Come on in. I'm recording right now, but I'm almost done with this problem, so give me just a second. So this is A, B, C. This is x naught, y naught, z naught. So we have 5, and then x minus 1, then minus 4, and then y minus, or plus 1, and then minus 9, and then z minus 1 equals 0. And this gives me 5x minus 5 minus 4y minus 4 minus 9z plus 9 equals 5x minus 4y minus 9z. Let's see if I can get this constant. -9 plus 9 is 0. So nothing. And this was number 28, so yay, I did my arithmetic right. Okay, so that's number 28. Time out. Give me a second. 29. So we're still finding the equation of plane that passes through a point. So hey, man, they just keep on giving us these points, making our lives so nice. And contains the line of intersection. Contains the line of intersection of the planes x plus y minus z equals 2, and 2x minus y plus 3z equals 1. Okay. Well, let's take a look at this one. We're trying to find the equation of some plane, right? It has a point on it, so we've seen something like this before. And it contains a line. There it is. The difference between this problem and the previous problem is that in the previous problems, we actually were given the equation of this line. We were given the parametric equation, and then in the last problem, the symmetric equation. So it's pretty easy for us to figure out the information we needed about this line because we actually had it. It was given. But this black line right here is actually not given to us here. We're told that this black line comes from the intersection of these two planes. So forget this plane for a second. We're not messing with this. Just focus your attention on this line. Where does that line come from? That line is the intersection of these two planes. So we have two planes sitting out here, and they intersect. It's probably hard to see on the camera, but they intersect. And where they intersect, they form a line. That's the line that we have here. So what we're going to have to do is we're actually going to have to find the equation of that line first from this. Then we can do the rest of the problem the way we did the previous two. So how do we find the intersection, the line of intersection of two planes? Well, what do we need to find the line? So to figure out what this line is, right, we need two things. We need a point on the line, and we need a direction vector, right? So can we find a point on the line? Well, a point that lives on this line lives on this plane and on this plane because the line is the intersection of the two. So if I can just figure out an x, a y, and a z that make both of these true at the same time, I will have a point. We've done something like this before. What I'm going to do is I'm going to take these two equations, I'm going to let z be 0, and I'm going to write out what I would have. X plus y equals 2, and 2x minus y would equal 1. And then I'm going to solve this system of equations for x and y. And this is going to be nice because if we just add down right now, we get 3x equals 3. Look at that. 3x is 3. Perfect. X is 1. Once I know what x is, I can come back up into this equation. It's 1 plus y equals 2. So that means y is 1. So if x is 1, y is 1, and z is 0, both of these equations should be true. So I have a point that lives on the line. The point is 1, 1, 0. That point lives on this line. Since that point lives on this line, I can use it as R naught. And R naught will be 1, 1, 0. All right, now I need the direction of the line. So going back to that picture, or actually I didn't draw a picture. We have these two planes hitting each other. So we have some line down here. Let me actually draw a line. Okay, this is the line that we're interested in, right? To find the direction of that line, what we'll do is we'll take the normal, and I've done this in class, so this is not new. Take the normal of this plane, the normal of this plane, I cross product them, and it will give me the direction of this line. So I need to take the normal of this plane and normal of this plane, cross them together. So V here, my vector V, my direction of my line of intersection is going to be the normal of this plane, I'm going to call it normal 1, crossed with the normal of that plane, I'm going to call it normal 2. And that we can find their normals pretty easily. The normal of this plane is 1, 1, negative 1. It's just the coefficients of x, y, and z. I'm crossing that with the normal of this plane, which is 2, negative 1, 3. And now I go ahead and get that cross product. I'm going to run out of room there. I'll put it up here. V is equal to, all right, so good old cross product here. Cover up the I. Get 3, take away positive 1, that's 2. Okay, cover up the j, so we get 3, take away negative 2, so that's same as 3 plus 2, which is going to be 5, but then it's the j, so we subtract it, so negative 5. And then cover up this, we get negative 1, take away 2, that's negative 3. All right, we're in business. We have now the information that we need about the line of intersection. I can now say that this line of intersection is this line right here. So I'm going to put R naught plus TV together. So it'll be 1 plus 2t, 1 minus 5t, and then 0 minus 3t. That is the vector equation of that line. I hope that you understand what I've done there, right? The vector equation of a line is R naught, the vector R naught plus TV. So putting that together, we get that. And I am on camera, barely. All right, so what we can do is we can start this whole problem over. And we can say, all right, find the equation of the plane that is, that goes through that point and contains this line. And now we just do what we did previously. We have a point, we have a line, we find a point on this line, we create a vector that goes from here to here. This is the point negative 1, 2, 1. We find the direction vector of this line, which we actually have it. It's the vector 2, negative 5, negative 3. We need a point on this line. We can get the point from right here. This is the point 1, 1, 0. And then we need this vector right here, so we go negative 1 minus 1 is negative 2. 2 take away 1 is 1. 1 take away 0 is 1. So we've got it all there. So the normal of my plane that I'm looking for, right, is going to be this cross with this. So it's 2, negative 2, 1, 1, crossed with this vector, 2, negative 5, negative 3, right? And then I'll need a point on the plane, which I already have, so I'm not even thinking about that. So when we cross these, my normal will be, okay, cover this up. So we've got negative 3, take away negative 5. That's the same as negative 3 plus 5, so that's 2. Cover up this one. We've got 6, take away 2, 4, but then change the sign, so negative 4. And then finally, cover this up. 10, take away 2 is 8. Hey, they're all divisible by 2. I think I'll use 1, negative 2, 4 instead. You could use that, but I'm just going to make it a little easier. So now finally, I'm ready to come up with the equation of the plane. A, B, C, x naught, y naught, z naught. So it'll be 1 times x plus 1 minus 2 times y minus 2 plus 4 times z minus 1 equals 0. And this gives me x plus 1 minus 2y plus 4 plus 4z minus 4 equals 0. X minus 2y plus 4z, 1, 5, oh, those are gone, so 1 is negative 1. Let's see, this is number 29. Check this real quick. X minus 2y plus 4z is negative 1. There we go. That's it. That's cool, man. I hope that made sense.
30. Find the equation. So we're still finding the equation of plane here.
Find the equation of the plane that passes through the points.
So it gives you 2 points. 0, -2, 5. Another point, -1, 3, 1. And is perpendicular to the plane lost my spot here. 2z equals 5x plus 4y. Just double check everything here. We've got 2 points and we've got a plane 2z equals 5x plus 4y. All right, so let me try and figure out what we got here. I'm trying to find the equation of this plane right here, okay? It contains 2 points. There they are. And then I can tell you that my plane is perpendicular to some other plane. So there's a plane sitting out here. The plane that I'm looking for must be perpendicular to this given plane. So that means they must hit at a right angle, like this. Okay. So what do I need to find the equation of a plane? I need a point. I need a normal vector. Do I have a point? Absolutely, I have 2 of them, so I'm not worried about that. I just need a normal vector. So I need a vector that's going to be sticking out of my plane, right? Here's my 2 points. The fact that this plane is perpendicular gives me something here. Let's take a look at this. Remember that this plane right here has a normal vector coming out of it. There, like this. And that is perpendicular to my plane. So if I were to imagine that normal vector without this plane being here, it's running perpendicular. The plane is perpendicular, the normal vector, sorry, is parallel. Do y'all see that? I think I said that wrong. The plane is perpendicular, that was here. The normal vector of that plane is actually going to be parallel to my plane. So this vector lives on this plane. So I can, to try and find this vector coming out, right, I can use this vector that's on my plane as one vector. I can connect these 2 points together and create a vector which I'll call u, okay? And so remember, I've got the vector from the plane, the normal vector from the plane that's perpendicular coming down here. I can always draw this vector. If I take those 2 vectors and I cross them, I will create this vector. Okay, I hope that makes sense. All right. So, what is the normal vector of this plane? Now, I don't want to confuse it with the normal vector of the plane I'm looking for. So I'm going to call this n, how about n sub p? So everyone knows this is the normal of the perpendicular plane. All right, the p is for perpendicular. So what is the normal of this perpendicular plane? Well, let's get everything to one side, all right? We have to get everything to one side first. So 5x plus 4y minus 2z is 0. So the normal vector is 5, 4, negative 2. So you notice if you didn't move the 2z over, you wouldn't have got that it was negative. So there's the normal of the perpendicular plane. So here's the plane I'm looking for. I have the 2 points that were on that plane, and I just came up with the normal of the perpendicular plane. I'm slapping it down onto this, and I can slap it anywhere I want. Here it is. Here's the n sub p. But because it's a vector, I can slide it around. So I'm just going to move it instead of there. I'm just going to attach it to that point right there. So there's your np. And then I'm now going to come up with a new vector that's going to connect these points together, which I'm going to call u. And then I know that if I cross these 2 together, I will get the normal out of the plane I'm looking for. So how about we come up with u right now? U will be the vector connecting our 2 points together. So it doesn't matter which way I go. I think I'm going to go from this point to that point. So 0 take away -1 is 1. -2 take away 3 is -5. And 5 take away 1 is 4. So that's this vector. So I've got my two vectors on my plane. Cross them now, and that's the normal I'm looking for. So the normal that I'm looking for is going to be the cross product of u and the normal of that perpendicular plane, which for me is the cross product of 1, -5, 4. That's this. And then the normal of the perpendicular plane, which I erased, but it is 5, hold on, let me look at, it's 5, 4, -2. All right, let's figure out what that is. That is covering up the I. Let's see, 10, take away 16. Is that right? 10 take away 16, -6. And then cover up these. I've got -2 take away 20 is -22, but then change the sign. And then cover this up. I've got 4, and then take away -25 is 29. That looks weird. Numbers is 30. Let me just double check that. Yep, that's right. Okay. So I'm in business. So this is my ABC of the plane I'm looking for. This is, I'll use this one as my point. So I have -6, x minus 0, plus 22, y plus 2, and then plus 29, z minus 5 equals 0. And if you simplify this down, you get -6x plus 22y plus 29z equals, I'm going to cheat here, 101. 101. There it is. That's the equation of the plane. So cool. How am I doing on time here? Trying to get through 31 and 32. So on 31, let's see if I can maybe help you get this without me doing it. It gives you the point 151. This point lives on your plane. And then you're told that it must be perpendicular, okay? The plane you're looking for is perpendicular to both 2x plus y minus 2z equals 2, and is also perpendicular to x plus 3z equals 4. So this one's a little different than the last one. You have a plane that you're looking for, right? You have a point on that plane. And then all you're told is that this plane that you're looking for must be perpendicular to this plane and a different plane at the same time. Well, remember we did in the last problem. We had, when we said that our plane is perpendicular to some other plane, we said if we took the normal off of this plane and dropped it down onto our plane, it would live in our plane. It would be parallel to our plane. And the other plane, okay, the other one, same story. If we take its normal and drop it down onto our plane, it will live and be parallel to our plane. So if we take the two normals of these two planes and drop them down to our plane, they both live in there. If I cross those two, I get a normal coming out of my plane. And then I have a point. So I have a point, and then the normal vector is just taking the cross product of the normals of these two. So without going through all the work, let's just say this. The point that I have is the point 151. The normal for the plane I'm looking for is the normal of this one, normal of plane 1, crossed with the normal of this one, the normal of plane 2. And what is the normal of plane 1? Move everything to one side. 2, 1, negative 2. And what is the normal of this plane? So notice there's no y in there. That means you have 1 in front of x, 0 in front of y, 3 in front of z. Cross these two together, you get your normal, you've got your point, plug everything in, you're done. How about 32? Find the equation of the plane that passes through the line of intersection of planes, blah, 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 and is perpendicular to. I'm going to let you do that. Yeah, I'm going to let you do that. How about 33? Okay, let's do 33. I'm getting hungry. 33. Find the point at which the line x equals 3 minus t, y equals 2 plus t, and z equals 5t intersects the plane x minus y plus 2z equals 9. All right. So this is the first problem since number 21 all the way to 32. You're trying to find the equation of plane, equation of plane, equation of plane. This one's totally different. This one is saying find the point where this line right here intersects this plane. So you have a plane, you have a line. Where do they hit each other? Where's that point? All right, well, in order to live on this plane, this equation must be true. In order to live on this line, these three equations must be true. So we know what the value of x must be. It must be 3 minus t. So if I come over here and I replace x with 3 minus t, and then go minus, and then I replace the y with this, 2 plus t, and then plus 2 times z, but z is 5t, that must equal 9. And what that'll allow me to do is solve for the variable t. 3 minus t minus 2 minus t plus plus 10t equals 9. So how many t's do I have here? 8 t's. And then 3 minus 2 is 1, and then take it to the other side, you get 8. Ooh, that's nice. T is 1. Is that the answer? No, because we want to know the point where they hit each other. So where is this point? It's the point that you get when you let t equal to 1. So I come back over here and I just let t be 1. If I let t be 1, I get x is 2. Let t be 1 here, I get 3. Let t be 1 here, I get 5. So you can verify for yourself. I mean, we know this point lives on this line, right? Because you just plug in t is 1 and you get this point. So that definitely lives on this line. Does it live on that plane? It should. Let's just check it. Plug in 2 here, so 2, take away y, 3, plus 2 times 5. Is that 9? Yes. So that point lives on this plane and it lives on that line, therefore it is on their intersection. 35. Determine whether the planes are parallel, perpendicular, or neither. If neither, find the angle between them. All right, so I'm going to do number 35. You're given two planes. x plus y plus z equals 1. Given another plane, x minus y plus z equals 1. And what I'm trying to figure out is whether or not these planes are parallel, perpendicular, or neither. So if we have two planes sitting out in space, they're either what, parallel to each other, they could be perpendicular to each other, or neither, right? They could just be off like that or something. So I'm trying to determine that. Well, let's talk about parallel. If they're parallel to each other, like this, then the normal vectors for both of these are parallel. So let's talk about the normal for this first plane. It's the vector 1, 1, 1. What's the normal for this plane? It's 1, negative 1, 1. Are these vectors parallel? Are they scalar multiples of one another? Is it possible to turn n1 into n2 by multiplying by a number? It's not possible. You can check it yourself. Okay, so plane 1 is not parallel to plane 2, all right? Because the normal vectors are not parallel. Remember, these don't have to be exactly the same. They just have to be off by a scalar, which they're not. Okay, so they're not parallel. How would you check to see if they're perpendicular? Well, if two planes are perpendicular, I hope it's obvious to you that their normals would also be perpendicular. So the question would be, are these normals perpendicular? So how do you check to see if two vectors are perpendicular? You dot product them, right? And you hope for 0. What's the dot product of these two vectors? Remember, dot product is a number. So you do first components multiplied, 1 times 1 is 1, plus second components multiplied, 1 times negative 1 is negative 1, and then 1 times 1 again is 1, and you get 1. And that is not 0, therefore they are not perpendicular. So plane 1 is not perpendicular to plane 2. So since they're not, it wants us to find the angle between them. So that means we've got these two planes that are hitting each other, but there's an angle between them, and we want to know what that angle is. Well, in order to find that angle, or the angle between the two planes is equivalent to the angle between the two normal vectors of the planes. So what I need to do is find the angle between those two vectors. So how do you find the angle between those two vectors? We go back to a formula we had. Theta equals arc cosine of, in this case, n1 vector dotted with n2 vector over magnitude of n1 times magnitude of n2. Whatever that is the angle between them. So this is going to be cosine inverse of the dot product of the two, which we did just a second ago, is 1. The length of n1, so this is where you do the square root of each of these squared, you'll get root 3. And then the length of this one squared is also root 3. So you get arc cosine of 1/3, which I don't have my calculator with me, is about 70.5 degrees. So about 70.5 degrees. That is the angle between the two planes. Now, number 37, which is the last problem out of the homework assignment, I'm going to let you do yourself, but I'll tell you what the answer is. Those planes in number 37 are parallel. So that's it. That's all I'm doing for this section.